Okay, good day. This is dual enrollment pre-calculus. I am Mr. McCulley, and this is lesson number 15, exponential models. Let's get right to it. So today we've got a couple things that we'd like to do. We're going to recognize the 5 most common types of models involving logarithms. We're going to use exponential growth and decay functions to model the data. We're going to use Gaussian functions to model data. We're going to use logistic growth functions to solve problems. And then we're going to fit exponential and logarithmic data to given values. So we have a couple of different types of exponential models that we want to talk about, all involving exponents and either e or ln. Um, these are in your textbook on page 221 if you want reference. And again, I wouldn't expect you to memorize all of these things, but I would expect you to recognize them. If you see something that looks like this, you should say, hey, that's a Gaussian model. Or if you see something like this one here, you would say, hey, that's a logistics growth model. Now they have different shapes, and they are kind of funny to look at. So um, I just stole a couple of pictures off the internet here and flashed them up here. So here is a graph of exponential growth. Here is a graph of exponential decay. The Gaussian model looks a little bit like this. Usually we call that the bell curve. Logistics growth model is usually applied when you have some sort of limiting value. A lot of times it has to do with population, and in this particular instance, you say they do label it as number of individuals. So as time goes up, the population starts to grow, and it grows a little bit steeper, and then eventually it levels off, and then there is some sort of top carrying capacity. Now, if you look at, just as an example, population of humans on the Earth, we're currently in this section, but eventually it's going to have to level off because we are eventually going to run out of space and resources here on the wonderful planet Earth. And finally, we've seen a couple examples of logarithmic graphs, and you'll see those there. All right, so there isn't really anything new here. It is all applications. So I've got 3 application type problems to go through, and I figured we just get right to it. So the first example comes from page 228, number 16. It says, and there's multiple questions on this one, but I just picked one of them. It says, complete the table for a savings account in which the interest is compounded continuously. So the moment it says compounded continuously, we're thinking A equals PE to the RT. And that is the equation that we will be using. It asks us to fill in for 2 different values. And so we can the annual rate and the amount in 10 years. Well, certainly we can't solve for both of them at the same time, and certainly one of these questions is easier to solve first than the other. So let's talk about which one should I solve first. Well, if I use the fact that the initial investment is 1,000 and the time to double is 12 years, the amount in 10 years, I really can't come up with anything there. Why? Because I have an initial investment, so I know what P is. So that's what this is. This is going to be P. This initial rate, well, that's my R. Here's a time, and the amount to 10 years, well, I still don't know that. And I also don't know rate. So I'm still without R. I'm still without a final amount. So it would be very difficult for me to solve for the amount in 10 years first. But if I know the time to double is 12 years, if the initial investment is $1,000, when it doubles, the A value becomes 1,000, or excuse me, 2,000. $2,000 when it doubles. Okay, so in this column, A has to be 2,000. So what I can do is I can solve at this rate first because I'll have all of the values except for R. So if I plug in, I'll go 2,000 into this PERT equation equals 1,000 E to the R times 12 because it takes that 12 T years for me to double. Okay, now we'll also see here is that For doubling, it really doesn't matter what the initial amount is. The time to double will always be the same. And the reason that is because if we're solving for r, the first thing that we would do is divide by the initial amount, which in this case is 1,000. And that'll give us 2 equals e to the, and let's rewrite it as 12r. That'll be a little bit easier. So it really doesn't matter how much you start with if you're talking about time to double, and you may see something like that later on a quiz or something, but just keep that in mind. If they give you a doubling time, but they don't give you initial amount, the shortcut is just make the initial amount 1 and the double amount 2, and then that saves us a little bit of work. All right, so we're solving for r. ln of both sides. That will allow us to apply the property that brings the exponent down. And in fact, ln e cancels out, and so I get the ln of e is equal to 1. And so the ln of 2 equals 12r. r equals the ln of 2 all over, oops, I did that incorrectly. Let's try it one more time. R is going to be equal to the ln of 2 all over 12. If I grab my handy dandy calculator, clear out what was there, the ln of 2 divided by 12 says that my rate is 0.057, will be 8 because we look at that to round. And remember, 3 decimal places unless one of those decimal places is 0, and then we'll take the third significant figure, or 3 significant figures there. All right, so let's see here. It'll be 0.0, what did I say, 578, I think. And so that is going to transfer to 5.78%. So 5.78%. So the amount in 10 years, this becomes a plug and chug equation now, because we're trying to find an amount in 10 years. And so I'm going to call this ANS. All right, so please keep that in mind, and I'm going to use that up here. And you really want to use, if you're doing two-step questions, try and use as many of the decimal places as you can. That'll give us a much more accurate final answer. So 1,000 E, and so I'm going to put ANS for my rate. Okay, so R equal to the ANS from the last problem in that case. And then 10 years, and I need 1,000, so this should be fairly easy to calculate. This would be a percent. We'll get, let's see here, 1,000, one more 0, second E, and then we'll go second answer. That's going to put those values in there times 10 years. Hit enter. So in 10 years, we'll have $1,781.80. And remember, this is money, so this is an instance where you would only round to 2 decimal places because we're talking about money. And that's the customary way we would report that. And I already forgot how much. All right, so 1781.80. And I think that's correct. Okay, let's check one more time before we move on. Yep, I'm happy with that. And so those are my 2 values. I should probably fill in the blanks as the directions said. And we'll move on. Okay, next one. The population P in thousands of Pineville, North Carolina from 2006 to 2012 can be modeled by P equals 5.4 e to the KT, where T is the year, and with T equals 6 corresponding to 2006, the population in, let's see here, 2008 was 7,000. It says find the value of K for your model and round your result to 4 decimal places. Now, I think that shouldn't be too much of a problem. Let's see here. If I talk, let's worry about this. So let's go through here. I have A equals PE. Let's see. In 2008, I have 7,000. So when T equals 8, and I know that because T equal to 6 is 2006, right? So my P would be equal to 7,000. And so if I plug in, I get 7,000 equals, oops, I made a mistake here. And hopefully you guys have already seen it, but it says the population P in thousands of Pineville, North Carolina. Well, if P is in thousands, then 7,000 would correspond to a P of 7. So I need to make that change right here to go along with everything else. So P of 7 equal to 5.4 e to the k with an 8. The only variable that I don't have right now is a k, so I'm going to solve for k. And the first thing I'm going to do that is I'm going to divide by 5.4. That'll give me 7 over 5.4 equals e to the, let's rewrite it as e to the 8k there. And then we're going to ln both sides. And so I've got the ln of 7 over 5.4 equals the ln of e to the 8k. And remember, ln e equals to 1. And so, and I'm going to flip here. So, we'll wait one more. So the ln of 7 over 5.4 is going to equal to the 8k. That's going to make k equal to the ln of 7 over 5.4 all over 8. And that'll give us a k value. So ln of 7 divided by 5.4. Close that parenthesis, all over 8. Hit enter, gives us 0.0324. So 0.0324, and that's our value for k. So now we have a new model in part B. We have a model that says population P is equal to the 5.4 e to the 0.0324. Now again, I'm going to use answer when I plug it in, but just for this right now. Now again, if 2018, if 2008 was 8, then 2018, that thing's going to give us a t equal to 18. So I'm going to plug that right in there. And again, this is the good news, and you'll see this over and over in the practice work. They're going to ask you to do the modeling in the first one, and then a plug and chug question in the second one. So let's see here, 5.4 second E second answer times 18, hit enter, and I get 9.6 or 682, 9.682. Now remember, this isn't our final answer, and the reason that is because P is given in, P is given in thousands. So our final answer, this is going to give us 9,682 people as our answer for that one. And let's make sure we do that correct. All right, next one. It says the number of yeast organisms in a given culture is given by the model, and it's given right here, where T represents the time in hours. So we don't really know what this is. We know there's some exponents, but it's in the denominator of a function. So if I go back here, it looks like this is most likely a logistics growth curve. So we're going to get a curve that looks something like this, where it starts off real low and then comes up and then levels out. And so we want to figure out what that is. Okay, so let's use a graphing calculator to start graphing this thing. And so I'll go to my y equals, and let's go alpha stat plot, and then we'll get a fraction there so we can put it in and have it look nice. So I get 663, oops, too many sixes, over, let's look at it one more time, 1 plus 72, 1 plus 72 second E And then let's look here. Negative 0.54 t. Negative 0.54 t. Now, if I hit graph on a standard window, I have a hard time seeing that, okay? So let's go back to a standard window. Let's go zoom, and then we'll mess with it from there. So we see that it goes up, and we got to eventually figure out where is it going to level off. Where does this thing level off? Well, if I hit my zoom, and let's make it, oops, I don't want to do that. Let's hit window. Sorry, let's go back. Standard. Oh, I'm messing up big time. Sorry. Zoom is what I want, and I want to zoom 6. We'll go back to the original. Now I hit window. That's what I wanted to do. Sorry about that. I just want to raise my Y values because I know it's got to start leveling off. And see, let's see if we can see it. So if I change it to 100, and I hit graph, it's still going up. All right. Well, let's make it maybe, it's still going up real fast. Let's make it maybe 1,000. And let's change the scale so I don't have so many tick marks. Let's make it to 100 there. And I hit graph. And now I see it starting to come up. Now it looks like I need to widen my X values, make my X values go a little bit longer. Let's make it go 50. And then we'll go by 5s here and see what we get. All right, now we've got that nice classic logistics curve. All right, so use a graphing utility to graph the model. We did that. Use the model to predict the population for hours at 19 and 30. Okay, well, we can do that. So we're going to go B here. We're going to say t equal to 18, or excuse me, 19. That's what I want to do. So for part B, I was doing real well up until this problem. For part B, t equal to 19, we're going to get y equal to, and then a t equal to 30, we're going to get y equal to. Okay, so let's go to our graphing calculator. Let's go second. Let's go second, and then table setup. We'll leave it on ask since we're typing in our numbers. And let's go 19, and then let's go 30. And so I've got 661 and then 663. So 661, 663, no decimal point there. I don't know why I put that in there. 663, and what are they? Just so we're cool. Organisms. Y-O for organ, not young or yeast organisms. And that'll be our answer there. All right, so according to the model, what is the limiting population? Well, let's look back at the graph here. 5, 10, 15, 20, 25, 30. At 30, we're almost that flat line. 5, 10, 15, 20. Well, here's 20. At 20, we're almost that line. So at 19, again, we're almost real close. And it looks like it's starting to flatten out and almost become a horizontal line. Now, if we look back at the, let's see here, what I want my equation here. Equation. If we look at the equation, we'll notice we've got that 663 at the top, and that's the numbers that both of those are close to, 663. Now, let's talk about it in terms of the equation that we have here. All right. So when t is 0, when you get 0 here, e to the 0 will be 1. 1 plus 70, or 1 times 72 is 72, plus 1 is 80 or 73, and then 166 divided by 73. Now, what happens as t gets bigger? Well, remember, as t gets bigger, the negative, I get 1 over e to the 0.54 t. So as t gets bigger, this thing goes to 0. 1 over e to the 0.54 goes to 0. So the bigger the t is, so again, looking at the graph, the further I go this way, the bigger my t graph is. The closer this expression gets to 0, 0 times 72 still gets close to 0, so 0 plus 1 is 1, and then 1 divided by 63, I said that backwards, 663 divided by 1 becomes 663. So the bigger t gets, the closer this thing gets to 663. So according to the model, the population, the limiting population would be 663 yeast organisms. Why does this example follow a logistics model instead of an exponential model? Well, again, we're talking, this is yeast organisms in a culture. You could probably have a couple of different reasons. You could say that is all of the space in the culture, or possibly 663 yeast organisms consume all of the food. So number of different ways you could answer that. All right, that's all I got for today. So the Super Fabu Star Wars fun fact of the day: in Revenge of the Sith, George Lucas thought it was going to be the last Star Wars movie ever, so he had a cameo in the opera scene, and he portrayed a blue alien diplomat. And so there's a picture of old George in his Revenge of the Sith regalia. You guys have a good day. I'll see you in class. Goodbye.